Sounds good. So thank you so much for having me today. Still Wednesday here in California, but it's a pleasure to be there on Thursday with you all. Today we'll talk about primordial black holes, and I will give you um, a few sort of variations on the theme of primordial black holes as dark matter. So for once in this talk, I will prove XKCD, usually a very authoritative source, wrong. And I will precisely deny the fact that black holes are ruled out as dark matter candidates. And I will claim that it is, in fact, interesting to consider primordial black holes as dark matter. I will try to give a perspective on where it is interesting to look for primordial black holes as dark matter. And I will then comment on what XKCD calls the no-see hums, the space cows, and the pyramids dark matter candidates. So first off, this is a plot that we've been looking at for quite a while in the community of people interested in understanding what the dark matter is made of. And this plot shows, as a function of the mass of primordial black holes in units of this solar mass, which fraction of the dark matter can be in primordial black holes. And if you look at this plot, it will look like in no parameter space there's any room for primordial black holes to be the dark matter. Well, this plot is wrong. And as I will argue today, it is interesting to ask the question, can there be enough primordial black hole around to be the dark matter in its entirety? And if so, what is the maximal fraction of dark matter in primordial black holes? So one thing that is important to appreciate in this plot is that the assumption is that all of the black holes are assumed to have all the same mass. And so these constraints only apply if you assume the dark matter primordial black hole function to be monochromatic or to be a delta function. So of course, the constraints depend on the mass function that you assume for primordial black holes. So again, this is what one has. If all primordial black holes have one single mass, this is what one gets if the mass function of primordial black holes is not log normal. And so it's a Gaussian with a certain width, centered around a certain mass, here again in units of the sun mass. And here is what you have if you have a power law mass function. So when myself and my associates first thought about the possibility to reconsider primordial black holes as dark matter, the question arose naturally. What is the mathematical function that maximizes the mass function of primordial black holes compatibly with a set of given constraints? Okay, so naively, this looks like a problem in variational mathematics. So in other words, calculus of variation. What is the mass function that extremizes a given functional? Well, the reality is a little bit more subtle, and technically the subtlety comes about because the mass function is positive definite. But that's exactly what we explored about a couple of years ago with my graduate student, Ben Lemon, and an undergraduate student at UC Santa Cruz, Jackson Yant. And Ben, who came to us in Santa Cruz with a master's in mathematics from Stanford University, actually answered that precise question mathematically in a very clear way. And the answer is that the maximal mass fraction of primordial black holes is given by a linear combination of n delta functions if you're given n independent constraints with calculable weights. And the reason why this is such a well-defined mathematical answer is that the problem is analogous to finding the minimum of the normal of a vector over a given convex hull that is given by the constraints at hand. And so this work really is entirely due to my graduate student, Ben Lemon. And so, for instance, if you're given this set of constraints, then the mass function of primordial black holes that gives you the absolute maximum mass fraction in dark matter from primordial black holes is given by this linear combination of delta functions. It's great when you have the joy of welcoming a graduate student with a master's in mathematics from Stanford who gives you the answer that seems to be right to a given problem. But it's better when you have an undergraduate student, and sometimes these undergraduate students come with blue hair, as in this case, this guy is Jackson Yant, who can verify that mathematical statement with a numerical analysis. And that's what Jackson did. And as you can see here, Jackson found exactly the same answer as the analytical answer that Ben provided. And so, varying the constraints that you believe apply to primordial black holes, you've got a given mass function. And that given mass function gives you the exact maximum fraction of dark matter that can come from primordial black holes. And so, as a result, given your choice of constraints on primordial black holes, you can certainly have 100% of the dark matter being primordial black holes. So that was great, and that's what we did in 2018. Now, I have been working on the question of what is the dark matter made of for many years. And for many years, I have contributed to the debate of, is this signal certainly from dark matter, or is it from some astrophysical effect or whatnot? So, when I started working on primordial black holes, a question that was very dear to my heart was the question, is there a way to make certain that a particular signal could be ascribed precisely to primordial black holes? And the answer is yes. And the answer is due to a famous Indian scientist, Chandrasekhar, who pointed out that you can only form a black hole from the collapse of stellar objects with a mass exceeding a certain mass, the Chandrasekhar mass, which is about 1.4 solar masses. So LIGO has searched for mergers of black holes, of which one is below the Chandrasekhar mass. But the question that myself and others in my group has asked is, if you're given a mass function, can you calculate what is the rate of events that contains a Goldilocks event, where Goldilocks event is an event where one of the black holes is featuring a mass below the Chandrasekhar mass. And so, given a mass function, you can calculate the rate for such events as a function of the mass fraction in black holes that are light and detectable by LIGO. So numerically, we can actually compute in the same way that it computed in the slides before the maximal fraction of dark matter that can be in black holes, what is the maximal and minimal possible event rate for events that contain a sub-Chandrasekhar mass black hole. And so here in the same sort of parameter space where we have the mass of the primordial black holes and a fraction of primordial black holes that are the dark matter, I show you here, when no constraints are applied, what are the maximal and minimal possible mass functions that provide, again, the maximum and minimal event rates with one event in the Chandrasekhar mass when you fix a given fraction of black holes with a mass in the detectable and light range. So when you apply all of the constraints, you get a slightly different answer. But what we calculated in this paper with the same collaborators, Ben Lemon and Jackson Yant, is the fraction of primordial black holes as a function of dark matter versus the light and detectable black hole mass fraction. What is the event rate that is detectable by LIGO that contains a Goldilocks event. And so in this plane, you see here in the maximal merger rate that a large swath of the parameter space contains one Goldilocks event per year at LIGO, where one of the black holes merging has a mass below the Chandrasekhar mass. And that is true even if the light and detectable fraction of primordial black holes is as small as 0.01%, okay, as long as these black holes form the bulk of the dark matter. Very good. So in addition to the mass, LIGO events, of which recently we learned a lot more than we used to know, also informs us about the spin of the black holes. And so this is a catalog that is now dated that myself and my collaborator, Nico Fernandez, Nico is from Colombia, and here's a picture of Nico the first time he saw snow as he moved from Santa Cruz to the University of Illinois, Urbana-Champaign. He looks a little bit intimidated by all that snow. Anyways, with Nico, what we studied is what we can learn about the nature of the black holes observed at LIGO from the effective spin that can be measured out of the wave function measured by LIGO in the merger rate. And so the effective spin here, let me remind you, is essentially a projection of the intrinsic spin of the black holes on the orbital angular momentum of the merging pair of black holes. And so the effective spin essentially depends on both the sets of masses and the set of spins and the orientations of the spins of the merging black holes. So the effective spin is a quantity that ranges from -1 to 1. So an effective spin of 1 essentially entails a large intrinsic spin for the black holes, as well as perfect alignment of the spins for the orbital angular momentum. Now, an effective spin of 0 entails either opposite orientations of the intrinsic angular momentum of the black holes, or the fact that the black holes have an intrinsically small angular momentum, have an intrinsically small spin. And finally, if the effective spin is -1, what you learn is that the spins are large and are anti-aligned. And that's fairly rare in black hole merger scenarios. So what we did with Nico Fernandez was to study what the shape of the prior probability distribution for the effective spin is in a variety of different scenarios. So this blue line here indicates what you expect from primordial black holes. And these three different lines correspond to three scenarios that the LIGO collaborations have considered when it comes to astrophysical black holes. So this low prior indicates an essentially low intrinsic angular momentum distribution, the flat, essentially a flat distribution of orientations, and high, a magnitude of spins that is intrinsically large. And in addition to that, you can also argue that spins are preferentially isotropically distributed or preferentially aligned. And that sort of depends on what you assume about the nature of the merging black holes. Whether they, for instance, belong to a cluster of stars, or they are random mergers of objects that do not have a common origin. So the effective spin priors that we determine for the different orientations and intrinsic spin distributions are shown here, and we could compare this with sort of a benchmark distribution that, following the LIGO collaboration, was chosen to be the low and isotropic spin distribution. So we can compare then that with the posterior distribution from the first 10 LIGO events, and from that we could construct ratios of log odds. In other words, how a given model compares to the low isotropic benchmark distribution. And what we found was that the primordial black hole case was slightly favored in terms of log odds compared to any of the sort of isotropic or aligned astrophysical black hole spin distribution. So that's pretty exciting because it arguably indicates that we might have, based only on the effective spin distribution, reason to believe that some of these black holes are of primordial origin. So of course, what we're looking at is extra events. And right now with Nico and others, we're looking at the evolution as a function of the number of events of these log odds ratios. And so if the truth is in primordial black holes, we expect, of course, the primordial black hole odds ratio to be constant, and the other odds ratio to decrease as a function of the number of events. Of course, if the truth is instead a low isotropic astrophysical black hole spin distribution, we expect different trends as a function of the number of events. Of course, you might also suppose that what we're looking at is a combination of astrophysical and primordial black holes. And so if that's the case, what we did was to calculate what the odds of a given fraction of primordial black holes versus astrophysical black holes is favored by the statistics of the observed LIGO events. And at present, what is favored is, again, a fairly large fraction of primordial black holes. And so which size this fraction is depends on what you assume for the rest of the black holes. But once again, assuming that, for instance, 50% of the black holes are primordial and 50% are astrophysical, as you increase the statistics, the maximum of this distribution squishes and moves towards the real primordial black hole fraction as your number of events increases. So the bottom line is that just looking at the intrinsic spin allows us to gain a lot of information about the nature and the origin of the primordial black holes versus astrophysical black holes in the LIGO merger events. So of course, while we do observe fairly low intrinsic spin in the LIGO merger events, the origin of this low spin might be even more exotic than the black holes being themselves primordial. And with an amazing Indian collaborator of mine, Akshay Galsazi, and again Fernandez, we considered a possibility that the intrinsic spin is depleted by the existence of a light bosonic particle that sheds angular momentum by the phenomenon known as superradiance. So superradiance is essentially an analog process to the just quantum field theoretical radiation of power from atoms. And what we did find was that as a function of the black hole and the intrinsic spin, there are absolute lower limits called Regge trajectories, again, as a function of the mass that you assume this light degree of freedom to have. So this, in the plane of mass versus intrinsic spin of black holes, represents where you're allowed to live. It's in the case of, say, 10 to the negative 11.7 EV mass for this light degree of freedom, you can only live north of this curve, and this looks like it's consistent with the observed data and so on. And again, this is primarily due to the great work of Akshay Galsazi, who's now moving to great things in his second postdoc. Now, one problem with this hypothesis is that the spin, the intrinsic spin of X-ray binaries, seems to be very large. Now, Akshay very smartly pointed out that might very well be explained by the fact that these X-ray binaries are very massive black holes. And so the large angular momentum modes of superradiance are actually not enabled. And so Akshay noticed that many of these low mass X-ray binaries actually align with the L=1 and L=2 orbits for superradiance. So maybe what we're looking here at is the possibility that indeed there is a favorite value for the mass of this light particle, and with some statistical assumptions on the intrinsic distribution of effective spins of these black holes, we are actually able to have a preferred mass for this axion-like particle, this light degree of freedom that is super radiated from black holes. So that's really interesting. And again, both of these studies will be updated with the recent load of new events from LIGO.
Stefano,
now, I argue that this study is wrong. Yes.
You have 5 minutes.
Very good. So I argued that this plot is wrong. So let me elaborate a little bit on that. So this plot is especially wrong in that low mass region for the following reason. So these constraints are primarily obtained from microlensing observations of M31 taken with the Subaru camera, Hyper Supreme camera on the Subaru telescope. And so if you look back at this 2017 paper, it has a variety of versions, and version after version, you see a bunch of corrections. So from the first to the second version, you see that first they eliminated wacky constraints from white dwarfs and neutron stars, and they corrected for the fact that you have wave effects. You have effects due to the fact that the wavelength of light that was used to probe these light primordial black holes was at the same length as the Schwarzschild radius of the black hole, so clear diffraction effects. But secondly, the Subaru collaboration pointed out that there are finite source effects that also carve into the region that is probed by microlensing events. Notice also that these constraints from femtolensing have been shown to be wrong because of a very important effect which comes from finite size of sources that have been looked at. And so this is fantastic work that I carried out in collaboration with Nolan Smith, a new graduate student at UC Santa Cruz that joined last year. And what we pointed out was that the stars that could be used to probe with microlensing black holes in Andromeda or in the Milky Way have to be much, much larger in size than the sun. In fact, they typically have to be 100 times larger in the sky than the sun. So what's the problem? Well, the problem is that if you have a star and you're trying to see the effects of a black hole that is transiting in front of the star and bending light and enhancing the flux of light because of lensing, if the star is very large, obviously you're not going to notice for a large swath of angular direction the effects of lensing because of the presence of a finite size source. Now, if you take that into account and you consider 4, 6, 8, and 11 times larger sources than the sun, you see how the constraints get weaker and weaker in the plane of PBH mass versus fraction of PBH that can be the dark matter. So what we did was to actually calculate what the statistical size of stars is in that survey, and we could actually conclusively prove that the constraints were vastly overestimated, with the conclusion that there's a large swath of parameter space that is still available for primordial black holes to be the dark matter. So how can we go after them? Well, one idea that we're working on is that these live black holes could be captured around pulsar systems and could modify the radio emission from pulsars. But what I want to point out to you all today is what happens to black holes that are very light and that are currently evaporating. So, evaporating black holes have been considered for a long time. These are light black holes with a mass around a comet or a pyramid, an Egyptian pyramid mass. Notice that the lifetime as a function of the Hawking temperature tells you that if you want these black holes to be the dark matter, they cannot be much hotter than 10 MeV. So what we really want to use, and what we did use with 2 other of my graduate students, Logan Marius, who's graduating this year, and Adam Coogan, who's a postdoc in the Netherlands, is a collection of MEV telescopes. So what can these MEV telescopes do in constraining evaporating black holes? Well, I don't have time to go through the details, but this is a spectrum that you get out of evaporating black holes. So there is a code called Blackhawk that does a great job in some range of masses to calculate the spectrum of evaporating black holes. There is a Blackhawk does a really bad job in extrapolating the effects of QCD degrees of freedom. And so what we did in a recent paper that appeared just a month ago was to calculate a correction to Blackhawk calculations that, just to give you an idea, this is the Blackhawk calculation, and this is the actual correct calculation of the emission for black holes with Hawking temperatures in the right regime. So what we were able to do was to show that actually the strongest constraints you have at the moment come from the COMTEL telescope. And secondly, that there's a variety of opportunities to really carve into the spectrum of black holes that could emit photons out of Hawking evaporation. And many of these telescopes are going to happen. And we are involved with GECKO, which is a telescope in the sort of mid-sized missions that NASA is probably able to fund without much effort. And so if you're curious about this, we have a paper coming up and a letter of interest in the SNOPAS process in the US that I invite you to look at. So I'm running out of time, so I'm not going to tell you anything about black holes whose evaporation can by itself produce dark matter particles. So these are very light black holes that evaporate, and the evaporation products actually are dark matter degrees of freedom by themselves. The last thing I want to tell you about is the possibility that evaporation does not end in the way that Hawking anticipated, which is essentially a black hole explosion, that evaporation actually stops. And evaporation is deemed to stop if black holes end up with an electric charge. This is a perfectly viable possibility. And if black holes have an electric charge, what happens is they become extremal and evaporation necessarily stops, because an extremal black hole has a vanishing Schwarzschild radius. And so necessarily, since there's no event horizon, there's no evaporation. And so you have a Planck scale relic that contains an electric charge. And what we calculated, again, with Ben Lehman, was, can we detect this charged Planck mass black holes? And yes, we can. And we can primarily with paleodetectors. These are detectors that use very, very regular minerals, very regular crystals, that upon the passage of a massive charged particle would exhibit a defect. And the detection of these defects could be telling us whether or not the dark matter is charged Planck black holes. So in wrapping up, I've talked about stellar mass black holes. I've talked about asteroid mass black holes. And here microlensing is a lot trickier than what we thought. I've talked about pyramid mass black holes. And here the best constraints are from COMTEL, and future MEV telescopes really have a chance to detect Hawking evaporation directly from black holes. And I didn't have time to tell you about how space cow Blake holes could produce dark matter by evaporation. And finally, black holes with a mass about a grain of salt could be charged and are very likely to be detectable, probably with paleodetectors, if not with direct detection experiments. And I'm going to stop here, and I'll be happy to take questions.
Thanks, Stefano. So I think we have time for maybe one or two questions. So first question is by Suchetna. So Suchetna, can you and ask your question?
No, okay. Thank you, Rishi. Thanks, Stefano. No, I was asking about the mass spin plane plots that you showed, and in those graphs, if you can kindly go to that plot.
I probably can. Let's see.
Yes, and so I was just talking about the spikes. There's the sharp step-like functions kind of.
Let's see. Are you talking about?
Yes, those steps kind of things in the plot. Yes, those things. Yes, that one. Next one.
Okay. Yes.
Next slide.
Yes.
Yes. You see this sharp kind of step kind of thing. What is the reason for that? That in some
the
mass
reason-
scales?
Yeah. So the reason for that is that you have constraints on which mass of black holes can actually super radiate a given mass particle. And so those edges correspond to different values of the angular momentum at which you can super radiate. And so, for example, if you see here, it's explicitly shown what happens for the L equals 1 and the L equals 2 angular momentum waves. Does that make sense?
Yes. Yeah. I was just talking about such sharpness. But yeah, thank you. Thank you.
Yeah, the sharpness just has to do with the detailed calculation of which mass is allowed to radiate a given angular momentum.
Okay. Thanks.
Okay, Bernard, you have a comment? Can you unmute yourself and ask?
Yes, indeed. Stefano, I'm Bernard Carr, and so it's nice to meet you. Obviously, I noticed all the slides which had some of my figures with "this is wrong" on, so I just thought I should react to that. I mean, first of all, I don't disagree. I mean, because the whole point is these constraints are constantly changing, and you showed the figure from 2017.
That's right.
You know, in many talks, I put great crosses next to the constraints that have gone away. So, for example, all the femtolensing has gone away, and the neutron star has gone away. And the other point to make is that you're absolutely right. Nearly always those constraints are for monochromatic mass functions. And I think in the paper in 2016, we explicitly say that how you got to modify the constraints when you have an extended mass function. And indeed, you showed some of those examples from one of the later papers. So it's fine to say that. And I just wanted to stress that. In fact, when I give my talk on Friday, I will give the most recent constraints, which are the ones I'm doing with my Japanese collaborators, which have got, well, they're very different. So I will show them there. And by the way, I do like all your terminology for these different types of black holes at the end. So thank you for that.
Thanks so much, Bernard. I really appreciate you. And of course, yes, please do consider that as the plot is wrong in its 2017 incarnation as of today. Thank you so much.
My most exciting moment when I was a young postdoc, a paper appeared with the abstract which said Carr is wrong, and I was so excited because I'd never seen my name in an abstract before, and I didn't care that it said it was wrong. So that's fine. Yep.
Cheers to that.
Yep.
Okay, so next question is by Kaushik. Kaushik, can you ask your question?
Hi, Stefano. So this is related to the plot that you are showing now. So when you go from this the monochromatic to this other mass functions, the constraints become stronger. Now, can you just quickly explain why that is happening?
Yeah. So in short, the reason is so first of all, these plots are not mine, but the reason is just that these mass functions are extended. Yes. And so. As you move from a monochromatic mass function to a mass function that samples a broader range of masses, you end up with a fraction of those black holes hitting a stronger constraints. So the constraints generically become stronger, but not on an absolute scale. So the point of the first part of my talk was that, just having one delta function is not the weakest constraint. Okay, the weakest constraint is when you have a linear combination of delta functions.
Okay, thanks.
Okay, we are running out of time. Maybe one last question by Patrick Dasgupta.
Rishi, maybe you can read out because some people have this microphone problem.
Okay, so his question was about whether the Planck-sized black holes will have both electric and magnetic charges.
Oh, very good. So generally, the mechanism by which we charge these evaporating black holes has to do with the fact that, in Hawking's evaporation scheme, you pair produce near the horizon, a particle and an antiparticle, and one of the two gets back onto the black hole. And so you end up charging the black hole that way. And since we don't have supposedly observationally any evidence for magnetic monopoles, then necessarily those black holes get charged by evaporation only by virtue of emitting particles with an electric charge. And so as a result, you cannot charge them magnetically. Now, this doesn't mean that there aren't exotic formation mechanisms that could charge primordial black holes with magnetic charges or with exotic other U of 1 prime charges. Okay, so you can have black holes be charged under both magnetism and other charges. But in what I'm considering, so this is just the simple-minded evaporation onto standard model charges that happens asymmetrically into positively and negatively charged particles.
Okay, thank you, Stefano. So I think we are out of time. Thanks very much for a wonderful talk.
Thanks. Cheers.